Dr. Wood, and in this video we're going to be talking about plotting data. Now the first thing to recognize about plotting data is that engineers use three different languages to communicate with one another about how the world works as well as how their solutions work. And those are words, like we're using now, mathematics, which is the purpose for these videos, and sketches, where we draw pictures. Now when we bring together mathematics and those sketches, what we get are plots. So we're using math and pictures to communicate bigger ideas. And so looking at this slide of different charts, you can see where engineers are using this for design, to develop different mental models, to help check their work. All of that happens through plots. Now when we do plots, we're most frequently going to be using a Cartesian coordinate system. I'm going to go ahead and abbreviate coordinate system. A Cartesian coordinate system is made up of two variables, and they are plotted orthogonally. You might say, well, that sounds terrifying. Two variables orthogonally plotted, but orthogonal plots are simply plots at right angles from one another. Most frequently in mathematics, we'll talk about this in terms of our variable x and our variable y. Our independent variable, sometimes called an IV for short, independent variable, is typically written on the horizontal or x-axis. And the idea here, most of the time, not always, is that this is the variable that we'll be manipulating directly as we think through our function or what we're looking at. The alternative to that is a dependent variable, in which once we've taken a variable, we've input it as our independent variable, we get this back from it. Our dependent variable, this is typically plotted on the vertical axis, or y-axis in this case. So if we put these two together, we often end up with either math functions which would look something like this. Maybe you've seen this notation before, where we'd say that the dependent variable y is equal to some function of x. Maybe this is a straight line function like mx plus b, or a quadratic equation. We put in an x value, we get a y value back, our independent variable, then our dependent variable. Alternatively, we can think about data as giving us something like matched pairs, where we'll have our x values and our y values, or more generally our independent variable and our dependent variable for a given set of data. And so either way, whether we're looking at a function or matched pairs, we can plot that on this Cartesian coordinate space. And typically we'll do that through matched pairs. So even if we have a math function, we'll pick some set of x, we'll solve for the y's, turn it into an xy pair, and then plot it on our chart. So now let's look at an example problem. The example problem that we're looking at today is from a tensile test. So this is something you'll do in your mechanics and materials lab in your junior year, in which we pull steel or aluminum specimens into two pieces, and we measure the displacement as well as the load required to do that test. It's actually quite fun, makes a big bang in the lab. Now when we have that data, which you can see on the slide, what we will do is we'll plot that, and we're actually interested in the slope of that first part of the line. So here you can see where I've broken down the problem in our problem-solving format that we use as engineers. We've been given xy pairs. We're being asked for both a plot and a slope, and I've outlined for us the process that we're going to follow in order to solve this problem. So the first thing we want to do is sketch our Cartesian space. Here's our independent variable and our dependent variable as we look at them here. We need to now label these axes. That's very important. As engineers, we're going to provide labels. So down here, we're going to have our strain, and we're going to provide units And this is a microstrain. This is our SI prefix 10 to the negative 6. There's another video on that if you have questions about it. And up here we're going to have stress. We use the symbol sigma, lowercase, and it has units of KSI, or kips per square inch, is the way that we've been given these units. And then we need to kind of put some scales on here, so 20, 40, 60. And you can see here where I've done my best to, on the board, chart out something roughly square. And this is why engineers often work on gridded engineering paper. Usually it's green. You'll be needing some of that for your classes when you come and you're doing your homework. All right, so I've sketched my Cartesian space. I've labeled it with units because as engineers we're working with actual properties that reflect a reality. We now want to plot the data. So if I look at my first data set, which you can hopefully see, my first point is at 4, so about halfway would be 10, so pretty low here. 4 KSI and 100 strain, so very low, right about here. So I'll just put a little dot there for that data point. My next one is at 21 and 500, so 21 is a little bit up, so somewhere about there. My next point's at 38, so not quite 40, a little less down, and 926, so a little less than 1,000. My next point is at 54, so about halfway between these two, maybe a little bit up, and 1360, so a little lower. And then finally I have one at 71. It looks like I need one more notch on my chart here. Okay, so that's going to be at around 71 and 1792, so about here. Now, I've plotted these by hand on this chart. Obviously, we could use Excel as our primary tool as engineers. That's probably what we'll use. You might be used to using a graphing calculator to do this sort of work. But when you get into your engineering classes, you're going to be using a scientific calculator, which doesn't have graphing abilities. So we'll want to be able to do this by hand or in a tool like Excel. So we've plotted our data, matching our x values, our independent value, which is our strain in this case, to our y values, which is our stress, which is our dependent variable. So for each strain, we should get a particular stress going on here. Now our next step is to sketch the line. If we were doing this in Excel or on a graphing calculator, we might go through and do a best fit line, which would use a least squares regression. But since we're just working on a whiteboard, I'm just going to freehand it. Hot shot with a ruler, something like this. So there's my line. That's not bad. Pretty good. Certainly for working on a whiteboard. Finally, the last thing we'd want to do is estimate the slope. We'll remember that slope is going to be the rise over the run. And so if I kind of pick some arbitrary points, it looks like this point right here has an XY pair of 1500 microstrain and 60 KSI. And we'll notice that it goes through the origin 0, 0, or close enough. And so my rise would be 60 KSI over my run. Now the slope in this case is going to have a material property called Young's modulus, or the modulus of elasticity, which is going to be the rise, 60 kips per square inch, divided by 1500 microstrain. All right, now that we've solved for our slope at 0.04 KSI per microstrain, we'll do some unit conversion. We'll have a later video on that, but real quick, just so you can see how that's done. We're going to multiply these values by 1. So a microstrain is defined as 10 to the negative 6th inch per inch, so it's technically unitless. And a KSI, kip per square inch, is 1,000 pounds per square inch, or 10 to the 3rd pounds per square inch. We remember that our negative power means that we can put it into the numerator and make it positive, so the net result of this 0.04 times 1,000 is going to be 40. 10 to the negative 6th becomes 10 to the positive 6 PSI once we have canceled all of our other units. And so our overall slope is equal to 40 times 10 to the 6th psi. A little extra there, but at the end of the day, this is what our plotting example looks like. I hope you have fun with your plotting example from dynamics.